Quantum supercomputers just took a massive leap forward. Scientists at Oxford University have created the first ever distributed quantum algorithm, linking separate processors into a single, fully connected system. This advancement eliminates past limitations and could change supercomputers forever. How does it work, and what does it mean for the future? For decades, quantum computing has been a futuristic dream, an exciting but unreachable technology that promised unbelievable power but faced impossible limitations. While traditional computers process information using bits, ones and zeros, quantum computers use qubits, which can exist in multiple states at once thanks to quantum mechanics. This allows them to process complex calculations exponentially faster than any existing machine. But there's a catch. The biggest hurdle for quantum computing has always been scalability. In order to perform truly unprecedented computations, quantum computers would need millions of qubits. But packing all these qubits into one machine has proven to be an engineering nightmare. The delicate nature of quantum systems means that increasing the number of qubits in a single processor leads to errors, instability, and massive hardware obstacles. This is where the new breakthrough comes in. Scientists at Oxford University have just achieved something no one thought was possible. They managed to link two quantum processors using a photonic network interface, effectively creating a single, fully connected quantum supercomputer. This marks the first ever demonstration of a distributed quantum algorithm, laying the groundwork for a new generation of supercomputers that can solve previously impossible problems. So, how did they do it? Instead of cramming more qubits into one processor, the Oxford team took a completely different approach. They split the computation across multiple smaller quantum devices and connected them using light-based quantum links. This method allows computations to be spread across a network of processors, making the system infinitely scalable. In theory, you could keep adding more and more processors, creating a quantum computing network with infinite processing power. To make this possible, the researchers used trapped ion qubits, which are individual atoms suspended in electromagnetic fields, acting as the fundamental units of quantum information. These were linked using optical fibers, allowing them to communicate instantly through quantum teleportation. This is the same bizarre quantum phenomenon that Einstein once called spooky action at a distance. Essentially, it enables instant data transfer between entangled qubits, even if they are miles apart. But what does this mean for the future? The implications are mind-blowing. With distributed quantum computing, scientists could break encryption codes in seconds, design new drugs and materials, and solve climate modeling problems that current computers can't even begin to process. It could also revolutionize artificial intelligence, allowing machines to learn and process information at unimaginable speeds. One of the most exciting parts of this breakthrough is how it brings us closer to the idea of a quantum internet. A super secure global network where data is transmitted using quantum entanglement, making it completely unhackable. This could transform everything from banking and cybersecurity to communications and government operations. To prove their system worked, the Oxford team ran Grover's search algorithm, a famous quantum algorithm that allows computers to search through massive data sets exponentially faster than classical machines. The fact that they were able to run this algorithm across two physically separate processors proves that distributed quantum computing is not just theory. It's real, and it works. But with every major advancement comes major challenges. Right now, quantum computers are still incredibly delicate. They require extremely low temperatures and precise environmental conditions to function. Scaling up a network of quantum processors while maintaining stability is going to require new physics insights and intensive engineering efforts. And then there's the competition. The race to build the first truly functional quantum supercomputer is heating up, with companies like Google, IBM, and Microsoft pouring billions into their own quantum research. Whoever cracks the scalability issue first will control the future of computing. And that means global power, military advantages, and economic dominance. One of the biggest concerns surrounding quantum computing is its impact on encryption and cybersecurity. Today's encryption methods rely on the fact that traditional computers would take thousands or even millions of years to break complex cryptographic codes. But quantum computers, using algorithms like Shor's algorithm, could break these codes in seconds. This means that all current security protocols used by governments, banks, and online businesses could become obsolete almost overnight. To combat this, researchers are racing to develop quantum-resistant encryption methods that can withstand the power of quantum decryption. However, the transition won't be easy, and there's a real fear that hostile actors could use quantum computing to launch cyber attacks before new protections are in place. But beyond cybersecurity, the potential applications of quantum supercomputers are staggering. In pharmaceuticals, quantum computing could simulate molecular interactions at an atomic level, revolutionizing drug discovery and cutting down the time it takes to develop new medicines from decades to just a few years. This could lead to groundbreaking treatments for diseases like cancer, Alzheimer's, and rare genetic disorders. In the energy sector, quantum computing could optimize power grids, improve battery technology, and help design more efficient solar panels. Scientists could run complex climate models with an unprecedented level of accuracy, allowing us to predict and mitigate the effects of climate change more effectively. For artificial intelligence, the integration of quantum computing could lead to AI systems that process and analyze data at levels beyond anything we've seen before. This could accelerate advancements in self-driving cars, medical diagnostics, financial forecasting, and even space exploration. AI powered by quantum computers could make sense of massive datasets instantly, detecting patterns and solutions that would take humans years to uncover. There's also the possibility of unlocking new realms of physics. Quantum computers could help simulate the early universe, test theories of quantum gravity, and even explore the possibility of parallel dimensions. This level of computing power could push the boundaries of human knowledge in ways we can't even begin to imagine today. Despite all this potential, there are still significant hurdles to overcome. One of the biggest is quantum error correction. Unlike classical computers, where errors are rare and easy to correct, quantum systems are incredibly sensitive. Even the slightest disturbance, such as a stray electromagnetic wave or a tiny temperature fluctuation, can cause a quantum computer to lose its state and make errors. Scientists are actively working on new quantum error correction techniques, but perfecting them remains one of the biggest challenges in making large-scale quantum computing a reality. Another issue is the cost. Right now, quantum computers are extraordinarily expensive to build and maintain. Only a handful of institutions in the world have access to functional quantum processors, and even those are still in the experimental stage. However, as technology advances, we may see the cost of quantum computing decrease, much like what happened with traditional computers in the 20th century. So, what does this mean for the average person? Right now, quantum computing may seem like something that only affects scientists, researchers, and tech giants. But the truth is, once quantum supercomputers become fully operational, they will reshape every aspect of our lives. From the way we bank and shop online to how we access medical treatments and communicate securely, quantum technology will be everywhere. In the coming years, we will likely see the first commercial applications of distributed quantum computing, with industries adopting this technology to gain competitive advantages. Governments will race to develop quantum capabilities to ensure national security, and major tech companies will integrate quantum-powered AI into everyday services. The shift to quantum computing won't happen overnight, but make no mistake, it's coming faster than we think. With Oxford's latest breakthrough, we are now closer than ever to making large-scale quantum computing a reality. Whether this happens in 5 years or 15, one thing is clear. The way we compute, analyze, and interact with data will never be the same again. The question is not if quantum computing will change the world, but how soon it will happen. Are we ready for a world where computers can solve problems beyond human comprehension? Where encryption is no longer safe, AI becomes exponentially more intelligent, and the very fabric of computing is rewritten. We may not have the answers yet, but one thing is certain. Quantum computing is no longer just the future. It's here. Quantum computing is no longer just a theory. It's happening. With Oxford's breakthrough, we're closer than ever to a world where supercomputers solve problems beyond human imagination. What do you think? Will quantum computing replace traditional supercomputers in the next decade? Let us know in the comments. And if you enjoyed this video, don't forget to like, subscribe, and hit the notification bell for more mind-blowing tech updates. See you in the next one.